All right, guys, I got the data in my calculator. Data taken from safety inspections about how many feet it takes to stop a car moving at different speeds. So if I'm going 4 miles per hour, it takes 10 feet to stop. If I'm going 24 miles an hour, it takes 93 feet to stop, apparently. It's a well-known fact that this data follows an exponential pattern. So use your calculator to find a least squares regression for the correct logarithmic transformation. All right. Change to an exponential function, all right, and give a prediction for a person who's traveling 67 miles per hour. Now, why is the prediction unreliable and therefore may be dangerous? Well, let's go one step at a time here. So I've got my data in the calculator, and I'd like to look at a scatter plot. So I hit stat. No, I don't. I hit second and y equals. That's what I do. That's the stat plot menu. So I hit number 1. And I'm going to turn that plot on. I'm going to go down. I've usually been looking at histograms to check normal conditions, but over here, I'm going to go to a scatter plot for list 1 and list 2. All right, I hit zoom and 9, and there is my scatter plot. And I stupidly did not get rid of the y equals log of the exponential function, so I still have that from a couple of minutes ago in there. Get rid of that, hit graph, there's my scatter plot. It definitely shows a curved form, not a linear form. You can see that it's curved. It's not a strong form, but it's linear. Okay, the least squares regression line after the data is transformed. Now we've decided it's an exponential curve. So what we do is we go to stat and edit. And I'm going to go to L3. I'm going to go up and hit enter. Once I hit enter, I want to take the log of the response variable. It's the log of all of these numbers. So I hit log and then L2. When I hit log and L2, I get a whole bunch of values. I'm never going to write these down. I don't care what they are. What I want to see is the scatter plot of L1 and L3 to see if it became linear. Okay, so I'm going to go to second and y equals. I'm going to hit 1 for my scatter plot, and now I'm going to change this from L1 and L2 to L1 and L3. I believe this will be more linear. So I hit zoom and 9 again, and it does look. I mean, you still have the overall shape with this kind of being a deviation, but this definitely looks a lot more linear than it did before. So now we want the least squares after the data is transformed. Okay, that's stat. Go over to calc. We do number 8 for linear regression. And I want to do this with list 1, but not with list 2. I want to do that with list 3 because that's the scatter plot that looked linear. So I'll go down to calculate and hit enter, and I get, it says, I'm going to put in parentheses up here, y equals a plus bx, but that's not really what's going on because I took the log of all the y's. So it's really the case that it's the log of y hat is equal to 0.922 plus 0.044x. Okay, an equation for the original curved scatter plot. Well, I would have to take this, and I would have to go 10 to the log of y hat is equal to 10 to the 0.922 plus 0.004x. And then the y's cancel, so I get y hat equals 10 to the 0.922 plus 0.004x. Now, I really do prefer to write this in a different way. Okay, so let me just kind of put that in like a little thought bubble. And I'd rather see this as y hat equals 10 to the 0.922 times 10 to the 0.004x. Now, the reason for that is because now it's in the form a times b to the x, which is generally, that's just a constant. That's generally the form for exponential functions. But sometimes your calculator doesn't like to do this. If this is a big number, it's going to turn this into a giant number, and it doesn't like to do that. It likes to crunch this number all in the exponent. Okay, predicted stop time for someone driving 67 miles per hour, well, that would be 10 to the 0.922 plus 0.004 times 67, right? And so I'll go 10 to the 0.922 plus 0.004 times 67. It's that easy, guys. Hit enter and I get 15.48. Did I do that right? I don't feel like I did that right. There's something wrong. 15.48, look at the data, and I put a 67 in. Something is not quite right there. I don't know where my notes are for this. Mr. Funny Guy thinks he's doing everything right all the time. Huh. Nope, nope, nope. Okay, found it. I got 0.92, Hang on. I think I have one too many O's here. So let me go back to stat and calc my least squares regression line. Do L1 and L3. It's 0.04. Now, why did you guys let me write 0.004? That's just stupid. 0.04. Guys, you know, you take your eye off the prize for 1 second here. So, let's try that again. 10 to the 0.922 plus 0.04 times 67. Okay, now I get a big giant number. And I'm looking at my previous notes, and I also had a big giant number. So the predicted stopping time is, I have 3,999.4 seconds. Or feet, I should say feet. Why is this prediction bad? There's no way that's correct. Why is this bad? 67 miles an hour? 67 miles per hour is nowhere near our data values. We have a word for that. I just use an x value that's nowhere near my x values. This is extrapolation. So may not be accurate. It probably isn't accurate. Look at that number. It's ridiculous. Okay. We have a book example to do next, which would probably be better than the Larson example, where I screwed up in the middle of the thing, and the numbers don't end up being all that real. Book example. I want to go to page 814, get all my notes and stuff out of the way, and look at number 43. Let's see what this thing has to say. 43, killing bacteria. Expose some marine bacteria to X-rays for time periods from 1 to 15 minutes. Here's a scatter plot showing the number of surviving bacteria on a culture plate after each exposure time. So after just 1 minute, there's a whole bunch of them left over, but if we leave them in there for 14 or 15 minutes, bacteria is having a hard time. See what I mean? Let's get rid of some bacteria. Now, below is a scatter plot of the natural logarithm of the number of surviving bacteria versus time. You guys, this is more like what you're going to do, not putting all the stuff in the calculator like I just did. This is what your stuff's going to look like right here. Okay, look at the x, time. Look at the fact that it's linear, and then look sneaky over here. What's going on here? It's the ln of the count. So they took that curved scatter plot from the last page, took the natural log of the y's, and straightened it out. Well, since that's the case, it must be an exponential function, right? Based on this graph, explain why it'd be reasonable to use an exponential model to describe the relationship with the count of bacteria and time. They're talking about this original scatter plot. That's going to be an exponential model. So they say explain why. Well, I'll explain why. Because when we took the ln of y, the form is linear. Take the log of the y values. If it makes it linear, that means it's an exponential function. Now, part B just says, here's the output from a linear regression analysis of the transformed data. Give the equation of the least squares regression line. Be sure to define any variables you use. So I'm going to take my line, and let's remember we took the ln of the y value, right? So this is going to go like this. ln of y hat is equal to 5.97. Well, they gave me a whole bunch of numbers, and so let's just go 316. We'll just give it a whole bunch of numbers for accuracy. Once you use exponential functions and logarithms, we should probably go more decimals than I went here, because exponential functions take off in a hurry, right? So a little bit of error turns into a lot of error when we round, rounding error. Okay, and then it's going to be minus 0.218425 times x. We took the natural log of y, and so that's what we have. And so I'm going to get my equation. It's going to go like this. Y hat equals, ready for this? Since I took the natural log, it's e to the 5.97316 minus 0.218425x. There you go. There's your equation. Now, again, I think I would rather have it as these two different spots. I think you could get away with this as far as I'm concerned for grading it. But again, I prefer as e to the 5.97316, which is just a constant, times e to the negative 0.218425x. That's more in the traditional form of an exponential function, a times b to the x. Now, let's take one more look at the original scatter plot and talk algebra for just a second. This is an exponential decay function, isn't it? Now, to be an exponential function that's decay, you either have to have a base that's a fraction or the exponent has to be negative. So take a look at what we just wrote down. The exponent is, in fact, negative. All right, so the last thing it says is use your model to predict the number of surviving bacteria after 17 minutes. Take one more look at the graph. After 17 minutes, there's not going to be very many of them. It's just about 0. So let's put a 17 in here. We'll go y hat equals e to the 5.97316 times e to the negative 0.218425 times our 17 minutes. Let's see how many bacteria are left after we go in there like Arnold Schwarzenegger, the Terminator, after these things. 5.97316. Please tell me some of you have seen that movie and I just didn't make a reference like an old man, because I can't take that. And then e to the negative 0.218425, and then it's times the 17. And somehow I get 9.58 bacteria. 9.58. That doesn't seem right to me. It just doesn't seem right. If I put it in here, I'm going to get the same answer. Let's just do that. E to the 5.97316 minus 0.21. That's all in the exponent, right? Yep. 218425, and that's 17 minutes. Wow, that's weird. How did that happen? Oh, I didn't put the 5 in there. Huh. What's going on here? 5.9, so there should be a 5 there. Well, I got an answer. If I put that, let's see, I'm going to bring this back up. And I'm going to insert this 5 here. See, that's supposed to be a 5.97. I actually like this answer better, but that's the right one. So I'm going to go second insert and put a little 5.9. And when I hit enter, I get that 9.58. I'm going to check that answer and see if it's right or not, but I'm not going to waste your time doing it. So I'll put a couple of homework problems from the book on Canvas for you guys. All right. One last day. We just got to do this one more day, guys, and we're done. Have a good day.